Hello, everyone. Today, we're going to travel to the farthest point science has reached, a place where even time and space hadn't taken form yet. Let's see what happened before the Big Bang and what could be hidden in the darkest moments of the history of the universe. Are you ready? Let's go. Brian Cox, a physicist, warned on the BBC Universe programme, "The last star will slowly cool down and fade away. After that, the universe will once again become a void, a universe without light, life, or meaning." We will explore the time before the Big Bang and the related theories. The disappearance of the last star will mark the beginning of an infinitely long and dark period. All the matter in the universe will be consumed by massive black holes, which in turn will evaporate and vanish into nothingness. Space will continue to expand outward until that faint light stretches further for more interaction. After that, all activity will cease. Is that weird enough for you? Some cosmologists believe that a dark and cold universe, similar to what awaits us in the distant future, could have been the source of our own Big Bang. First topic. Let's take a look at physical matter. If we want to explain the origin of stable materials made from atoms and molecules, surely none of these existed at the Big Bang, or for hundreds of thousands of years after it. We currently have a clear understanding of how atoms form from simpler particles, and know that they were created under conditions when the universe cooled enough for more complex materials to stabilize. We also know how these atoms later transformed into heavier elements and found their place within stars. However, this understanding doesn't answer the question of whether something came from nothing. So let's think much further back. The first long-lived particles of matter, protons and neutrons, formed together to create atomic nuclei. These particles appeared only 1/10,000th of a second after the Big Bang. Before that pivotal moment, no matter truly existed. But physics allows us to trace the timeline backward, a backward journey into the physical processes that preceded any stable matter. Our physics leads us to the theory of the grand unification. We have now properly entered theoretical physics because we cannot generate enough force in our experiments to study the processes that were occurring at that time, and we must rely on theories. The first plausible hypothesis is that the physical universe formed from a primordial soup, a term coined by one of the scientists to explain the origin of life on Earth, with a short lifespan containing quarks and the components that make up protons and neutrons. At that time, both matter and antimatter existed in almost equal amounts. Each type of matter, such as a quark, has an antimatter or mirror image that is nearly identical to itself, but differs by just 1 degree. However, matter and antimatter annihilate each other when they collide. In other words, these particles constantly appear and disappear. But the question is, how did these particles first come into existence? Quantum field theory tells us that even in a vacuum, which seemingly has no energy, physical activities occur in the form of energy fluctuations. These fluctuations can lead to the creation of particles that disappear shortly after. This may seem more like a mathematical ambiguity than real physics, but such particles have been observed in countless experiments. In other words, the vacuum state of space-time is constantly bubbling, with particles continually created and destroyed from nothing. But perhaps all of this is really trying to tell us that the quantum vacuum, despite its name, is more than just nothing. Now let's ask, where did space-time itself come from? Now we can rewind time further and go back to the ancient Planck era, a time early in the history of the universe when our best physical theories break down. This period occurred just 1/10,000,000th of a trillionth of a second after the Big Bang. At this stage, both space and time were subject to quantum fluctuations. Physicists typically deal separately with quantum mechanics, which governs the world of tiny particles, and general relativity, which applies at large and cosmic scales. However, to fully understand the Planck era, we need a complete theory like quantum gravity that merges these two. We still do not have a complete theory of quantum gravity, but efforts such as string theory and loop quantum gravity have been made in this field. In these attempts, space and time usually appear like the waves on the surface of a deep ocean. What we experience as space and time is the result of quantum processes that operate on a deeper, microscopic level, and these processes have no specific meaning for us as beings rooted in the macroscopic world. In the Planck era, our understanding of space and time breaks down, and thus we can no longer rely on our understanding of cause and effect. Nevertheless, all the proposed quantum gravity theories describe something that was occurring in the Planck era. But where did this come from? Even if causality does not apply in any other form, it may still be possible to explain one part of the Planck era in terms of another. Unfortunately, even the best laws of physics today cannot provide an answer. Until we move towards a theory of everything, we cannot give a definitive answer to this question. The best answer we can confidently give at this point is that physics, so far, has found no confirmed examples of something coming from nothing. To truly answer the question of how something can arise from nothing, we must explain the quantum state of the entire universe at the beginning of the Planck era. Ultimately, all attempts to answer this question remain speculative. Some of them, like a designer, look towards supernatural forces. Other explanations remain within the realm of physics, such as a multiverse that includes infinite parallel universes or models of a cyclical universe that is born over and over again. Roger Penrose, the Nobel Prize-winning physicist of 2020, has proposed an intriguing but controversial model for a cyclical universe. Any cosmological model where the universe follows infinite or unspecified cycles is called a cyclical model, which is referred to as conformal cyclic cosmology. Penrose drew inspiration from an intriguing mathematical relationship between a hot, dense, and small state of the universe, just as it was during the Big Bang, and a very cold, empty, and expanded state of the universe, as it will be in the distant future. According to Penrose's fundamental theory, these two states become identical as they reach their ultimate boundaries. Although this theory may seem contradictory, the complete absence of matter might give rise to all the matter we see around us. In this view, the Big Bang emerged almost from nothing. This nothing is the result of a vacuum of matter in a universe that was swallowed by black holes, which then themselves evaporated into photons and eventually disappeared. Therefore, the entire universe originates from something that we can say is almost the very nothing we refer to. However, this nothing is in itself something. In fact, it is a physical universe, even though it is empty. How can it be that this state, from one perspective, is a cold and empty universe, and from another perspective, a dense and hot universe? The answer lies in a complex mathematical method called conformal scaling, a geometric transformation that changes the size of an object but leaves its shape unchanged. Penrose demonstrated how the cold, dense state and the hot, dense state can be related through such rescaling, so that their spacetime shapes match, though not their sizes. Admittedly, it is difficult to understand how two objects can be identified in this way when their sizes are different. But Penrose argues that size, as a concept, has no meaning in such physical environments. In conformal cyclic cosmology, the evolution of the universe moves from old and cold to young and hot. In fact, the dense and hot state arises from the cold and empty state. But the why of this is not so familiar. It is not only size that prevents the connection between these two states, time is just as important and valuable. The cold, dense state and the hot, dense state exist at different timescales. The cold, empty state, from an observer's viewpoint, persists forever in its own time geometry, while the hot, dense state generates its own temporal path. This definition might help in understanding how the hot, dense state is created non-causally from the cold state. Perhaps it is better to say that the hot, dense state emerges from the cold and empty state, or maybe it has settled within it. These are specific metaphysical ideas that have been widely explored by philosophers of science and in quantum gravity. In quantum gravity, cause and effect relationships break down. Within our scope of knowledge, the distinction between physics and philosophy becomes challenging. Empirical evidence, conformal cyclic cosmology, provides precise answers, even if theoretical, to the question of where the Big Bang came from. However, even if Roger Penrose's viewpoint and theory are confirmed with future advancements in cosmology, a deeper philosophical question may arise, one that we cannot yet answer. Where did the physical reality itself come from? Where did the entire system of cycles emerge? Ultimately, we arrive at one of the biggest and purest questions of metaphysics. Why does something exist instead of nothing? However, our focus here is on explanations within the domain of physics, not metaphysics. There are three comprehensive options to address this deep question of how the cycles began. On one hand, there may be no physical explanation for this question. These cycles may either repeat endlessly, with each one being a new universe, or there may be a single repeated cycle, in which the beginning of each cycle can be described by its end. Both of these approaches avoid the need for any event without cause, because in physics, nothing is without cause. Penrose also imagines a sequence of infinitely new cycles that are actually linked to his interpretation of quantum theory. In quantum mechanics, a physical system is a superposition of many different states happening simultaneously, and when we measure it, only one is randomly selected. For Penrose, each cycle involves quantum events that occur in different ways, meaning each cycle is different from the cycles before and after it. This is actually good news for experimental physicists, as it may give them the opportunity to glimpse into the old universe and detect weak remnants or radiation anomalies from the Big Bang, as observed by the Planck satellite. The key point of Penrose's view is the existence of infinite new cycles. However, there is a natural solution to turning multi-cycle cosmology into a single cycle. In this case, physical reality consists of a single cycle, from the Big Bang to an infinitely empty state in the far future, which then reshapes itself around the Big Bang and repeats the same universe. In the end, many mysteries remain to be uncovered, and we may never reach all the answers. But it is these questions that make the universe a fascinating place, full of new discoveries. So always continue searching for the truth with curiosity. If you found this video interesting, be sure to like it and subscribe to see more videos.